So to a large extent, this talk is going to be I'm going to say roughly the same things I said in my last talk on local to global, but in a slightly different context. As we were discussing, the general strategy is to try to match up the two sides of Langlands is to construct sufficiently many objects on both sides that sort of generate everything, and then compare those. It's very rough. Oh yeah, I forgot to mention, since we're all tired, and there are only so many categories of sheaves that one can learn about in a week, there are going to be a lot of lies in this talk. But that's okay. So the question basic question I want to address. I'm sorry?
You mean lies? By lies, you mean leave?
All right, so the basic question I want to address is how do we construct D modules on bin G. So this is a complicated stack. D modules are very abstract things, but ultimately we'll see that we can construct a lot of these from representations of affine Lie algebras. So first of all, so the answer to this, as was in the last talk, was going to be to do some kind of a local to global construction. This? Yeah. I don't know. I don't think there is one. I certainly don't know of one. I mean, this is more. Somehow, geometric Langlands has this feature that it combines arithmetic and conformal field theory, and this is the conformal field theory side of things, and not the arithmetic side of things. And they don't seem to. Well, this I don't know, Dennis.
No, I want to stress this point. It was not, I don't know if you were here. So Sasha Bareman asked me, well, on this Galois side, this operation of going from quasi-co-loxis to representations to him looked kind of tautological, and the other side was doing Whittaker. But this is the Langlands dual side of the story. So I don't know if you were in the discussion.
That's the automorphic side.
Yeah.
Well, exactly. So I mean, I don't know if you were. So in fact, this Langlands correspondence picture looks symmetric. So this is automorphic. This is Galois. So here you have Whittaker, and here you have representations. Rep G-check. But we'll complete this picture to here you have Kac-Moody, and here you have what's called opers. Now, Kac-Moody vis-a-vis Banji plays exactly the same role as rep G-check versus quasi-co-loxis G-check. And opers vis-a-vis loxis check will play exactly the same role as Whittaker. And in fact, you can deform this picture.
Write it down?
He wrote it, come on. Well, it was there, remember?
Yeah.
Moreover, there's a deformation of the story, and this is called critical level versus infinite level, where things become symmetric. So
all of this is fine, but this has no analog in the automorphic picture.
Exactly. So yes and no. So namely,
I don't know to construct classical representations which are unramified at all places.
Oh yeah. Obviously it doesn't, but I mean, it has the following sense. So this functor fits into a family of functors depending on the parameter at this level. And when you go to infinity, what you hit is rep G check going to loxis G check. Okay, rep G going to loxis G. Let's say on the same side. It's just now we're considering that parameter being equal to infinity. But now let's take on our side a parameter to infinity. So it will be rep G connecting to loxis G. And that is your Galois data. So that when you think of local versus global Galois parameter, this is what we're doing. So again, if you go for simple, there's a P1 of parameters. Here we are at point 0, and we're doing this. But if you were at point infinity, you'll be reading off Galois. So that's the not. It's never automorphic. It's kind of it's Galois-like. Okay, let me just say it like this. Okay.
Would it be easier to appreciate what you're saying after we see the construction?
Yeah.
That's the idea.
So let's say one word. Okay, so classical theory of automorphic forms, so the roles of automorphic representations of Galois representations is very separate. They don't exhibit similar features. So what happens here is Bun-G has both the features of something automorphic, we consider Eisenstein series, blah, 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 all this stuff. But also it has some Galois features. This is the Galois feature. So in the kind of so geometric story has both things combined. And so and only one at a time has an analog.
So I didn't quite get it.
Okay, sorry. Yeah, maybe
Yeah. Yeah. So the first thing I wanted to do was give a kind of local to global description of D modules on Bun-G. So, well, we've seen some examples of this already. So, well, the run space will play a picture. So we can consider so we can take the infinitesimal version of the Hecke groupoid. So we have this stack over the run space. Let me just define it. But this is a version over the run space of the familiar Hecke stack, but formally completed at the diagonal. So this is so we take how do I say this? Let's see, what do I want to say? I'm at a loss for notation. Let me describe the fiber at a point on the run space. So S is a point. So S is some finite subset of X. So what we do is we take G bundles cross G bundles. So it's a pair of G bundles which is identified away from the set of points and formally completed at the diagonal. So for each S, we have one of these, and these very nicely over the run space. So so we get is one of these. So this lives over. So we get a groupoid over Bun-G times the run space. Which we can further project to Bun-G. Yeah. So the idea of this thing is, again, you should really compare this to the infinitesimal groupoid of Bun-G. So if you think about what the infinitesimal groupoid looks like, then what it does is it's going to be a pair of G bundles which are infinitesimally close together. This is what is parameterized by the infinitesimal groupoid. This is a pair of G bundles that are infinitely close together that are also identified away from the set of points. So you might imagine that as you sort of integrate over all the possible sets of points where you allow them to be different, then you'll recover back the infinitesimal groupoid. And indeed, this is what happens. So, well, how should I say this? So we can consider quasi-coherent sheaves on Bun-G, which are equivariant with respect to this. So specifically, what this means is you pull back. You look at the two pullback maps that you're supposed to give an isomorphism, and there's coherence data associated with it. So I don't know. Hey, Dennis, can I get rid of this intermediate thing? Would people object? because then it's no longer a groupoid. But
It's okay.
okay, yeah. So let me. It's just like a groupoid, but not where things are not necessarily invertible. But it still makes sense to consider it an equivariant category. Anyhow, one way or another, we can consider this thing. And so the theorem is that there's an equivalence of categories between these Hecke equivariant quasi-coherent sheaves. And D modules on Bun-G. Yeah.
So what is not a groupoid?
Pretend I never said that. But
So what did you write on the right of the board on the top? So consider
this.
Are these invariants?
So equivariant.
Eigen.
No, equivariant quasi-coherent sheaves. So with respect to the streak pullback, so in other words, it's the data of a quasi-coherent sheaf. So an object here is a quasi-coherent sheaf here, together with identifications of the two pullbacks here, and all the coherence data that goes along with it. So, well, I don't know. No, it's not in any way special for Bun-G. It's a general statement. So Bun-G is one of these things that you get as flat sections of something. And anytime you're in that situation, there's a similar story. But probably it's not worth saying right now, since everybody is tired, including me. But we've seen another version of this. Well, I guess we haven't seen it, but if you read the notes from my last talk, a version of this appeared when Bun-G was replaced by local systems.
And if we do it just for 1 point instead of run, will the theorem still be true?
For 1 point, so
Not over the run space.
but 1 point of the run space or 1 point of x?
Well, over x.
No, certainly not. And I mean, I told you exactly what you would get. You would get things which are equivariant with respect to the operation, where you don't allow arbitrary infinitesimal modifications. You only allow modifications at those particular points or point that you chose. But well, you have to allow the point to move.
Yeah, around x.
Oh! You want to take over x? No, the problem is, see, that won't work either, and you shouldn't expect it to work because x is not contractible. So you'll pick up. So we're in the derived setting. So you're picking up the topology of x as the point moves around. Somehow the key point is that the Ron space is contractible. So none of the powers of x none of the configuration spaces that build up the Ron space are contractible, but the Ron space itself is contractible, which is why you're able to get results like this. So, yeah.
So if we take a quotient of Bun-G by this infinitesimal cake,
Yeah.
we won't get precisely the realm of Bun-G.
Oh, you will, except you have to be careful about what you mean by take the quotient. It's not, a priori, it's not the sort of thing you're allowed to take quotient by. But,
Is this similar to the parallel transport business where you have x over x to the round, and you take x times x over x to the round, and this is like a groupoid over x, and you want your quasi-coherent sheaves to be equivariant with respect to this on x?
yeah, so this,
A similar flavor?
yeah, so this is so that thing that you're describing is what I call the infinitesimal groupoid. So again, we define D modules to be sheaves on the de Rham stack, but you can describe them in terms of descent data on X. So it's, in other words, it's sheaves which are equivariant with respect to a certain groupoid. And that groupoid, if you see, the term is the formal completion of X at the diagonal, which you can interpret as giving the relation of identifying fibers at infinitesimally closed points. Here it's similar, except there's a restriction on which infinitesimally closed points you identify, parameterized by the Ron space. So, well, based on what I said, it's sort of obvious that there's a functor in one direction. Into this category. Namely, you can just take your D module, you can forget it, you can only think of it as a quasi-coherent sheaf in Bun-G, and then you can pull it back to Bun-G times the Ron space. And because it was equivariant, because the quasi-coherent sheaf was equivariant with respect to the entire infinitesimal groupoid, it'll be equivariant with respect to this as well. So this functor, so I don't know. Well, so that's one side of the equivalence, and the, well, so there is a, so how shall I say it? More generally, let me just introduce some notation. We have a functor. Oh, whoops. I'm sorry, I meant run. Drum everywhere. So we have a functor from D modules on Bun-G. Two well quasi-coherent sheaves on Bun-G, tensored with D modules on the Ron space. So that's just pulling back to here, which are equivariant with respect to this Hecke groupoid. So now, note, this is not the same category as this, but there's a functor, and it has a left adjoint. Let's call it lambda. So there's a way to take sheaves on Bun-G cross the Ron space which are equivariant with respect to this thing and build a D module on Bun-G. Note that this is a pretty strange kind of functor. All right. I'm sorry? Well, because this it generalizes in the sense that this functor factors through this one. There's an obvious map here. Just pull back, and well, I don't know. No, I guess the new statement is that this has a left adjoint. That's reasonably behaved. So somehow the idea is, if we want to construct D modules on Bun-G, that if we want to do it in a local to global way, this category right here is a good recipient for any functor which will construct D modules for you. So
Is the second map just the composition of the first map with a projection?
which map? The adjoint map or this one?
No, is the top line
The top line?
a consequence of the third line?
Yeah. Or vice versa.
Oh, that's true. Both statements are true. So this one is not a consequence. There's a statement here that there's a left adjoint. That this, I think, doesn't guarantee that. But you can certainly,
So which way, can you draw an arrow to which direction is the diagram?
both are true. So you can factor this way, or you can factor this way. The point is, if you go here and then go back, it's the identity. It's a localization, for the reason that the Ron space is contractible.
So the no bonus condition is nothing.
What's that? No, both are equivariant, but they match up.
And lambda is surjective.
What's that?
Lambda is surjective.
Oh yeah, which is fully faithful. So this guy is fully faithful. What's that?
I can't read the target of this arrow.
The target of this arrow?
Can I just read that?
Yeah, it's quasi-coherent sheaves on Bungie, tensored with D modules on the run space, equivariant with respect to this as opposed to sheaves on this. All right. Okay, yeah, so we're going to take this to be the recipient of this functor, which will give us D modules. And now let's talk about the source. The source will come from Kac-Moody representation. So Dennis yesterday described this category L, and there should be a level, but because it's late and everybody is tired, I will ignore all issues of level. Is that okay? So roughly speaking, we take this to be in toe of P so not all the symbols are defined yet. The naive classifying space of some version of the meromorphic jets on G and sheaves on this. So this is the formal completion. Of jets of meromorphic jets along just regular jets. Oh.
Why did you say naive classifying space?
What's that?
Why did you say naive classifying?
Well, it's just you don't cheat for fun. That's all. Just take the simplicial object from the pre-stack. So far we're not allowed to take incoherent sheaves on such a thing, which is another thing I want to worry about. But how to do this is explained in the notes to Dennis's talk yesterday. But let's pretend everything is okay. Oh, and so why is this a reasonable definition?
This is okay because the transversal directions are
Finite type.
finite type.
Yeah. So there's So yeah. So pop quiz. Why is this a good definition? Anybody?
We discussed it yesterday.
Yeah. So we discussed this yesterday. So the point is that KLG is equivalent, at least at a point. This is equivalent to G hat. Let me just write it like this without specifying the level. Comma G of O, the Harish-Chandra category of G hat, G of O representations. So the way I wrote it, this makes perfect sense. This object makes perfect sense over the Ron space. So B makes sense. Meromorphic jets was something that we constructed over the Ron space. So we actually obtain one of these factorization categories. So note, KLG is a factorization category. And okay, so so let's try to compare it with the one that I just erased.
So when you write representations there, you mean all these conditions that get
What do you mean by all the conditions?
there were some conditions for
Well, so these are
for
no, this is the derived category.
So that was kind of a low-tech version, but if you do it in code, that won't take into account.
Yeah, that's built into the definition essentially, or a consequence of how INCO is defined on such things. So that yeah. Well, you can take a different definition, and then maybe you may have had a pre-existing idea of what these things were, and the claim is that that's probably, if your idea is reasonable, then this is an isomorphism. And Dennis explained yesterday in the talk actually how to construct this in a different way, and the assertion here is that this is equivalent.
And why is it G check rather than G K double parentheses
G of
I mean,
oh, why G hat?
get
no, this
Kac-Moody,
This is
potential.
so there's a version so it's a what's that?
No, but why is it not G?
Well, I want to be implicit about the level, which is why I is that confusing?
The fraction field of O. So
Either ignore it or don't.
Ah,
So
because G check it was also the
yeah, so I have no level, but I wanted to be ambiguous about that deliberately. Anyway, there's a way to twist this to build in a level. And so I guess I should preface this. I'm ignoring all issues of level, but only for ease of exposition and notation, not for any essential reason. All right, so we have this category. So let's try to compare this to this category that was on the board here. Well, so we have we have these. So we can write B jets neuromorphic G, or at least int co, in the following way. So we can start with just, so we have B of jets of G, and this maps to, this of course maps to B of jets neuromorphic of G. So we can write the corresponding So we can consider the corresponding groupoid, namely look at the iterated fiber products of this thing. So we have this B jets. I'm sorry. We have this B jets of G, and then we have this B jets of G crossed over these funny B jets meromorphic of G and so on. So the point is, we can give this another name. Let's call it the local Hecke, infinitesimal Hecke stack. So this is exactly analogous to the local version of the infinitesimal hackstack that I defined yesterday for log_sys, except now it's for G bundles without any kind of flat connection. So this is the thing that classifies pairs of G bundles on the formal disk together with an identification infinitesimally and an identification on the formal punctured disk. So the observation is that there's a map of groupoids from between these guys. So just pulling back, we can start with sheaves here and pull back to here. So pulling back, we get a functor. This thing? Whoa, whoops. Thank you.
What's the name?
Oh. What's that? Lock. So.
What was there nice about the presentation?
What's that?
What was there?
No, it was a question which I'm about to answer. The question was, I took this map and I looked at the corresponding groupoid. It's this one. So what are equivariant sheaves here? So clearly I can pull back equivariant sheaves here to equivariant sheaves here. So let me erase this. So the claim is that we can consider int coherent sheaves on B jets G equivariant with respect to this local hackstack, that this is isomorphic to just this Kazhdan-Lustig category. So it's the same as int coherent sheaves on this. So this is some kind of a descent statement for int coherent sheaves. So yeah. So does that answer your question? So this is exactly just the KL category. So just pulling back. What's that? Yes. So induced from compact objects from G of O representations. I'm going to say something a little more about that in a minute. So pulling back, we get a functor. Well, let me call it log sub G, which is going to be the composite of this pullback and lambda, which is the thing that sends equivariant sheaves on bun G cross Thorne space to just equivariant sheaves on bun G. So we have this functor. So remember where this is. Quasi-coherent sheaves, bun G. So we obtain this kind of localization functor. So you may have seen a version of the localization functor for Kazhdan-Lustig representations before, and certainly this looks much more complicated. So, I'm sorry? No, there's no hat. That's a phantom. It's a phantom hat. So well, what does this bias? This kind of description of this localization functor. Well, the point is, we can look at there's a slightly easier version of this functor, which is for quasi-coherent sheaves. So we can take G of O representations and produce from them quasi-coherent sheaves on bun G. So there's a functor sort of quasi-coherent localization from, well, let me write it like this: quasi-coherent sheaves on jets into BG into quasi-coherent sheaves on bun G. So this is just the functor. It's the same functor I wrote down for local systems yesterday. So we have this correspondence. So there's an evaluation map. And P, so this O localization, this is just you pull back and then you take Durham push forward. Question?
Can you comment a little bit now on the analogy with the upper right part of on the Galois side? So
yeah, so this should look exactly like the. So this is a diagram I wrote down yesterday for rep G check going to quasi-coherent sheaves on local systems, and well, it sort of deforms to that. I mean, it's the.
So, but you didn't have a diagram like the one on the right.
This one?
Was it? So so you have this factor from quasi-coherent sheaves on local systems up to representations.
Yeah.
Adjoint.
Yep.
Was that obtained by Urban from some?
No, that was. So this is the this diagram is the analog of that functor we had yesterday. So I made a statement about D modules on local systems yesterday, and this was implicit in that. It was I never got to defining the functor. Had I gotten to that, I would have written a diagram very much like this, where jets would have been replaced by jets horizontal. So somehow it's a very similar procedure. So the point is, well, this is a much more trivial thing, but well, we saw yesterday. What's that? Oh, whoops. Thank you. I even wrote Durham here, and this Durham. Yeah.
It's equivalent to localizing first to the Grassmannian of Med and then to
Oh. So I'm not quite sure what you mean, but the standard way of doing this is say you pick a point and you look at a bun G with full level structure at that point. Yeah. So this is equivalent. Well. Yeah, this gives the same answer, certainly. So as I said, you might wonder why you need a different description than the one you gave. So let me try to give an answer. Let me try to answer that question. So we saw yesterday that the corresponding functor for local systems was had an adjoint that was fully faithful. So we can ask, does this well, I sketched the proof, and it didn't really use. If you followed the proof, you'd notice that it didn't really use very much about local systems or meromorphic or horizontal jets into BG or stuff like that. So you might wonder, maybe such a statement is true in this case. So you might wonder, maybe such a statement is true in this case, and it's not quite true, but it's almost true. So what is true is that so this localization functor has a right adjoint co-localization O sub G such that, so it's not going to be continuous and it's not going to be fully faithful. And the failure of it to be fully faithful is exactly the same as the failure of it to be continuous. So, and the reason for this failure is that the stack Bun-G is not quasi-compact. So yesterday, in order to establish that this co-localization functor was fully faithful, well, rather that it was continuous, and to use this dualizable categories machine, we used the fact that local systems was a quasi-compact stack. So Bun-G is not, but we can restrict to a compact open, quasi-compact open. So quasi-compact open. And J lower star followed by the co-localization functor. This is fully faithful. So this is a right modification of that statement in the case of G bundles. But now, a corollary of all of this is that if you stare at this diagram for a minute, you'll see that that the two localization functors, one for quasi-coherent sheaves and one for D-modules, are compatible. In other words, if you start with a quasi-coherent sheaf, or if you start with a representation of G of O, and you build a quasi-coherent sheaf on Bun-G out of it, and then you can freely make a D-module out of that. You can induce. That's one thing you can do. Alternatively, you can start with your same representation, induce it to a representation of the Kac-Moody, and then localize it to a D-module. Those agree. So a consequence of that is the same exact statement for the D-module localization functor. So loc G has a right adjoint from D-modules of Bun-G to this K L category. Now I'll emphasize that this is all happening over the round space. Whose restriction to a quasi-compact open U inside of Bun-G is fully faithful. So we don't get a fully faithful functor, but we get something very close to it. And in fact, if we look at this localization functor dually, it doesn't generate this category of D-modules on Bun-G. We don't get the whole thing, but we get something very close to it. So if we restrict to any quasi-compact open, we do get the whole thing. So let me rephrase that. So just tautologically rephrasing this is, in other words, for any quasi-compact open, G, the functor, first we do loc, then we can Durand pull back. From this Kac-Moody category to D-modules on U, that this functor is a Verdier quotient. In other words, it has a fully faithful adjoint. So this is a... So at the very least, it tells you that by localizing Kac-Moody representations, we don't get the whole category, but we get pretty close to it. Oh, all right. In the last few minutes, I guess I'd like to. Yep.
Has anything occurred so far that isn't just a part of the general localization format, as opposed to something that really uses this Hecke groupoid? Like, is there something going on beyond the framework of the Harish-Chandra modules?
Beyond the framework of what?
Of Harish-Chandra modules and actions.
Yeah. So we really, I mean, it's to deduce this corollary. I think we needed more than Harish-Chandra. I don't know how to see that from Harish-Chandra.
So because this is very
Yeah. So I think this is the statement where just having this picture with Harish-Chandra modules is not sufficient, or at least I don't know how to deduce it from that.
Yeah. Well.
So this is the.
Okay, but the existence of the right adjoint at least is okay.
Yeah, sure. I mean, it's just formal, right?
Yeah. And
so, well, I mean, how do you check that it's fully faithful? Otherwise, I mean, I was comparing it with this O module localization.
Yeah.
So, well, anyhow. I mean, plausibly, you can run a similar story, but anyhow. So you get this kind of result. So I wanted to say something about what, maybe recall if you've seen a version of this localization functor before, kind of what it does to concrete things. So I said that it's compatible with the induction functor from O modules to D modules, or from representations of G of O to Kac-Moody representations, but it's not compatible with the forgetful functor, at least, but it is in some cases. So let's try to see what happens. So the point is, one advantage of having this functor, which I just erased conveniently, is that representations of Kac-Moody is something relatively concrete. So we can write down explicit objects in this category. So let me tell you how to do that. So suppose we take sort of some number of points in X and the same number of modules in well, KLG. So let me just write it more concretely as G of K, G of O representations. So by the general yoga of factorization algebras, what we can do is we can build well, let me first say it a little more simply, a sheaf on the round space, a D module, with the following properties that, let's call this script M. So at one of these xi's, the fiber at one of these xi's is this module Mi, and for other fibers is the vacuum module. So we can build such a thing on the round space, and then this is, so a priori this is just a D module on the round space, but hopefully it's not hard to believe that such a thing carries an action of this of the version of this guy over the round space. So really, this lies in this category that I called KL sub G, which is quasi-coherent sheaves. And B jets near G hot. So we can actually get it here, and so we can ask what is look in Gmod. So any guesses for what the localization of this thing will be? Well, maybe that's an unfair question. So let's say what the fibers of this are. So suppose, for simplicity, let me take the trivial bundle. And then I guess the claim is that if we take the fiber here, this is just the chiral homology of this is the Kac-Moody guy. This is the factorization algebra that Sam described. Did that actually appear in your talk? Okay, that Sam would have described. All right, I'll say something about it in a minute then. That's a shame. So it's chiral homology anyway. There's a version of chiral homology for not just a factorization algebra, but a factorization algebra in a module. It's like, well, hopefully that's not too hard to imagine. So, well, it's essentially let me just say it like this. So it's the de Rham cohomology over the Ron space of that sheaf M that we constructed. So V is the vacuum module. Which is the induced representation from G of O to G of K of the trivial representation. All right. Well, this guy is a factorization algebra that corresponds to this whole thing. It has the property that, well, if you take all the mi or no mi at all, the fibers will be just a vacuum module. So I don't think I have time to say anything else. Am I out of time, by the way? Or do I have a few minutes?
At this point, it doesn't really matter. So.
Do I have a few minutes still?
You do. Yeah.
Okay. Okay. What's that? So the fiber over a different bundle, yeah. So this Kazhdan-Lustig category. So the fancy way. So let me give an abstract answer and a down-to-earth answer. So which one would you like first? Anyway, the abstract answer is this: that this Kazhdan-Lustig category is a sheaf of categories over this space, and then a G bundle gives you a flat section here. And so you can pull back, and then so it's the pullback of this object to. So you can pull back and you can interpret the result as a D module in the Ron space, and it's going to be the de Rham cohomology of that. Maybe that's not such an enlightening answer, but what's really going on is that there's an action. By either this Harish-Chandra pair or that formal group on everything in sight. And so, well, if you have a sheaf with an action of G and you have a G bundle, you can twist it. It's a standard construction. So that's really what's going on. So really, I would put P here. That's the only change.
These aren't literally D modules on non-space either, right? It's on some marked non-space. Just ignoring it.
They are also D modules on the Ron space. You can push forward. It's okay. What's that? It'll look like this. It won't factorize, though. I never said it was a factorization algebra. So I wanted to describe a slight variant of this construction also, which is that, well, remember this KL category. This KL category is compactly generated. So let's say for a particular x, but all of it really compactly generated. So there's a dual, and in particular we can consider the unit inside the tensor product. So ignoring issues of level, let's pretend that the dual is just that it's self-dual. So really there's a shift in level. So I'll write this is approximately equal to KL of. So this has another name. It goes under the name of CDO sub G. So this is chiral differential operators for G. So for the experts, there's of course a shift in level by the Tate level, but let me ignore that. So this forms a factorization algebra in, well, roughly oh, whoops. I'm sorry. Sorry about that. I've been fast and loose about these anyway, but let me at least get the notation right. So for the same reason, well, in particular, it gives us one of these things that we can forget the fact that it's a factorization algebra. It's just, we can think of it as just a sheaf here. And so we can apply, oh, whoops, on the square. So I think I'll wrap up here. And the last statement I want to make. What's that? In the middle? Yeah. So what I needed. So what I needed about M was that if I have a G-bond that. So roughly M is a thing such that this category acts on it. And alternatively, the formal group corresponding to the completion here acts on it. So there's a general formalism which says that if you have a sheaf with an action of a group, and I have a bundle for that group, I can twist the sheaf by the principal bundle. So it's a usual associated bundle construction. And this gives the description of the answer. So these are really conformal blocks for these things. So the thing I wanted to say, so another name for this, I think I'm okay because this word appeared already. Another name for chiral homology is conformal blocks. So the last statement I want to make, and it's essentially, and it's more or less the same statement that I made yesterday about localizing the push forward O, localizing the push forward of O, that was the diagonal bimodule. Here we get something similar. So we have this unit, which is roughly the push, which is delta functions at the diagonal. So the localization of CDO, this is delta Durham lower star of, I don't know what to call it, omega upon G, so delta is the diagonal map from bungee to bungee across bungee. So one thing that this formalism immediately outputs is that when you localize chiral differential operators as a D-module on the square of bungee, what you get is again delta functions on the diagonal. So I think that's actually all I wanted to say, unless.
So.
Yeah.
Okay, so this is the computation where something happens, right?
This one?
Yes.
Oh.
And I mean, this is what's responsible for the fact that the localization is fully faithful, whatever. So.
Well, I mean, those are, in this case, those are kind of equivalent statements.
Mm-hmm.
So once I say that it's fully faithful, the proof is not this of the fully faithfulness statement. This is a consequence, at least the way I'm presenting things.
Well, okay, but can we?
You can also go back and deduce that statement from this one.
Yeah. Let's say I want to avoid this infinitesimal Kac groupoid just for simplicity. So this localization of the CDO is something induced. So I can compute it through your modular.
No, CDO is not something induced.
It is something induced from a integral representation. It's the regular.
Oh, sorry. Yes. Okay. Yeah. Great. Okay. Great. Yeah.
So I just have to compute the localization of functions on G of O. It seems. Well, how hard could it be? I just have to find omega of 1G.
So Sam, what do you want to do? So you want to?
I want to just do this computation directly without infinitesimal Kac groupoid.
The localized CDO.
Yeah.
This one.
Let's maybe release everybody and then we'll discuss it, because I think maybe people are craving to go ahead.
Okay.
Yeah.
Dennis, is this our?
Let's release them.